Hi, this is Gary Prunus. I'd like to spend some time talking about temperature measurement accuracy and some practical things we can do to improve the accuracy of our measurement. When I'm doing a formal presentation to a group on this subject, I'll oftentimes start by asking if anybody in the room needs to measure temperature accurately. And as you might imagine, responses are all over the map, but there is one response that I hear repeatedly, and that is no, plus and minus 1 degree is fine. And that response is actually quite helpful in that it tells me that this group really doesn't appreciate how difficult it is to measure temperature to that degree of accuracy. Plus and minus 1 degree in a process environment is a high accuracy temperature measurement. And you have to do everything right if you're going to get close to that degree of performance. There are processes that we know for sure need high accuracy temperature measurements. And then there's a whole bunch of temperature measurements that we make that we know we don't need high accuracy. In those, perhaps we just want to look for trends. Is it going up? Is it going down? Is it staying the same? But then there's a whole bunch of temperature measurements where perhaps we're uncertain whether we need to improve the accuracy of the measurement. And for those applications, I would recommend that you ask yourself, do I need to calibrate these loops? Do I need to verify that these loops are correct? Have I put these loops on some PM schedule for routine checks? If the answer is yes, then perhaps you should consider implementing some high accuracy techniques, because the same techniques we use to achieve accuracy also achieves a more stable temperature measurement. Things like selecting the right sensor reduces drift. Selecting the right measuring instrument reduces drift. Using 4-wire RTDs reduces drift caused by lead wire. And if you reduce drift, you push out the frequency of your calibrations or verifications, and that directly impacts operating expenses. So improving accuracy and reducing measurement drift can be related and can have measurable results. So what are we going to look at in this talk? Well, we're going to take a look at selecting the right temperature sensor for the application. We're going to look at ways we can eliminate error caused by our external environment. We want to reduce error caused by lead wire between the sensor and the measuring instrument. And then, can we reduce error at the measurement itself? In this example, we're concerned about maintaining temperature uniformity of the product in this vessel. The process folk have given us a goal of a product uniformity of plus and minus 4 degrees Fahrenheit at the operating temperature of 250 Fahrenheit. We're going to use 2 sensors so that we can better indicate product uniformity. If we were to choose a type J thermocouple, because that's our plant standard, we may not achieve our goal. One of the thermocouple standards that we use in the US says the type J thermocouple accuracy is plus or minus 4 degrees Fahrenheit at the operating temperature. So our product uniformity could be perfect, but two type J thermocouples could read 8 degrees differently and cause us to report to operations that were out of spec. At this point, you could calibrate out the difference in the sensors and put together a regular PM program to make sure the two sensors stay in sync, or you could choose a different sensor. If you choose a Class A 100 ohm platinum RTD, the error is only 0.7 degrees Fahrenheit. Two RTDs could differ by as much as 1.4 degrees Fahrenheit while reading the same product temperature, and that is way better than the 8 degrees difference that we could have had with two type J thermocouples. I should say that I am very prejudiced in favor of RTDs for many reasons, and all those reasons will be explained as we drill down into this topic of measurement accuracy. Selecting the best sensor for the application greatly affects the accuracy of the measurement, and I'll always reach for an RTD when the process temperature allows. I started my career in the steel mills of Pittsburgh, so I know all too well there are many measurements we have to make that are outside the capability of RTDs. So let's take a look at some of the options we have when we're using thermocouples. From one of the temperature standards we use in the US, ASTM E230. If we look at the column marked 300 Fahrenheit, we see that a standard grade thermocouple, a J or a K, has an uncertainty of about plus or minus 4 degrees Fahrenheit. You can improve thermocouple accuracy by using special tolerance, or often called premium grade wire, when building your thermocouples. Basically, the reduced error is achieved by using wire with higher purity alloys. At 300 degrees F, a special tolerance thermocouple error is about plus or minus 2 degrees Fahrenheit. If we were to use a 100 ohm platinum Class A RTD at 300 Fahrenheit, its uncertainty would be plus or minus 0.8 degrees Fahrenheit. If you think of these past three slides, you could loosely say that going from a standard grade thermocouple to a premium grade thermocouple, you cut your error in half. And then going from a premium grade thermocouple to an RTD, cut your error in half again. So again, we're back to sensor selection being very, very important to measurement accuracy. Thermocouples may be wired back to a PLC or DCS And when they are, you have to use thermocouple extension wire. And unfortunately, the thermocouple extension wire is yet another source of measurement error. Look at the column marked standard error. The standard grade J or K extension wire adds another plus or minus 4 degrees Fahrenheit of uncertainty. You can buy premium grade extension wire that has half the error, just like the premium grade thermocouples. But still, it's plus or minus 2 degrees Fahrenheit. These errors shown here are when the wire is new and pure. Over time, wire gets contaminated from the atmosphere in the plants, and perhaps the wire is exposed to temperatures greater than or lower than the ranges shown here. And in both cases, the error caused by the extension wire simply gets worse. Do you check to see how much error is caused by thermocouple extension wire? Most people I know ignore the entire subject until operations calls up and declares that this temperature measurement is a problem, or perhaps there's a catastrophic measurement failure. We all know thermocouples fail, but thermocouple extension wire also fails. When it does, it has to be replaced. If you replace the extension wire with new extension wire, you're just reintroducing the error it causes. You're simply perpetuating the same problems. You may have to live with thermocouples, but you don't have to live with thermocouple extension wire. And I'm a big proponent of replacing it with other technology. The other technology to use to replace thermocouple extension wire is either temperature transmitters or remote I/O hardware. Both of these use copper wire to transport their signals back to the control system or the data acquisition system, and you can expect copper to last the life of the plant, which is not true of the thermocouple extension wire. Modern I/O products have the same performance characteristics similar to transmitters and can be a lower cost alternative versus transmitters. When you use transmitters or I/O products, you still need short sections of extension wire between the sensor and these products. And in those cases, I recommend using special grade thermocouple wire and further minimize the error contribution to by the extension wire. If you've not studied this topic, you might be lulled into thinking that RTD extension wire, which is copper, does not introduce error into the RTD measurement. But RTDs are resistors, and copper wire is resistance. So in fact, copper wire can cause significant error in an RTD measurement. There are many contaminants in the typical process plant that causes corrosion, and that corrosion changes resistance. Resistance change in lead wire contributes to error. To eliminate lead wire error, the solution is to use 4-wire RTDs, and here's the story. In the microprocessor-based world, We measure RTDs by exciting them with a constant current source. Then we measure the voltage drop across the RTD. We use Ohm's law to solve for resistance. And then we apply the RTD curve to read the results directly in temperature units like degrees Celsius, degrees Fahrenheit. The function of the constant current source is to maintain the same excitation current even though the resistance in the loop is constantly changing. When the industry first used 2-wire 100-ohm platinum RTDs, we realized there was a significant error due to lead wire resistance. Basically, what we're measuring is the sum of the RTD plus the lead wire resistance. And if you have long leads, that error can be very significant. For that reason, the industry developed the 3-wire RTD measurement. The third lead is added to the RTD, and we're going to make this temperature measurement by making 2 voltage measurements as shown, V1 and V2. The important thing to remember is that these, quote, voltmeters are high impedance. So for all practical purposes, there is no current flow through that third lead. Thus, R2 never enters into the equation, or the lead wire resistance of that third leg never enters into the equations. When we measure voltage 1, that gives us the value of lead wire resistance R1. When we measure voltage 2, that gives us the value of the RTD plus the lead wire resistance R4. And then we subtract the 2. And as long as the lead wire resistances R1 and R4 are the same value, they cancel one another, and we're left with the value of the RTD, and that is an accurate measurement. When we're concerned about measuring accuracy, we have to realize that too many things work against making R1 and R4 identical. Wire gauge intolerance, work hardening of wires changes resistance. Even if no human error takes place in the installation, corrosion constantly works against us and perhaps is the major contribution to guaranteeing that R1 never equals R4. So if the lead resistances are not equal, what happens? If the resistance imbalance in the current carrying legs is as little as 1 ohm, a 100 ohm platinum RTD has an error of more than 4.5 degrees Fahrenheit. If you're trying to achieve a plus and minus 1 degree measurement accuracy, this corrosion is standing between you and success. You can spend your life calibrating this out or eliminate the error totally. And the 4-wire RTD eliminates the error completely. Remember, the voltage measurement is high impedance. So for all practical purposes, there is no current flow through lead wires R2 and R3. Therefore, there is no voltage drop. So when we measure the voltage as shown, it's delivering only the resistance of the RTD. Unlike with the 3-wire measurement, we never measure R1, we never measure R4, we don't have to subtract them, we don't give them an opportunity to create an imbalance, and therefore the resistance in the current carrying legs creates no error in a 4-wire RTD measurement. When you use 4-wire RTDs, the lead wire can be any length, it can undergo constant resistance change, and still it causes no measurement error. You do have to make sure that the total resistance does not exceed the drive capacity of your constant current source, but with 4,000 ohms of drive, that's hard to do. With your lead wire error gone, you can go back to focusing on selecting the right sensor and selecting the right measuring device to further eliminate error sources. In my travels, perhaps the only logical objection to using 4-wire RTDs comes into play when there is a legacy input card that can only accept 3-wire RTDs. By today's standards, that's very old technology, and perhaps alternatives should be considered. If, for whatever reason, 4-wire RTDs is not in your future, consider the next little trick. Switch to 1,000 ohm platinum RTDs. We saw earlier that 1 ohm of resistance imbalance in the current carrying legs produces more than 4.5 degrees air. When you're using 100 ohm platinum, if you switch to 1,000 ohm platinum, that same 1 ohm of imbalance reduces the air by 1/10. In the chart in this slide, we've expressed the air as a percent of span for a measuring instrument that is span 0 to 300 F. One ohm of imbalance with 100 ohm platinum would be a 1.6% air, which is huge. Change that 100 ohm platinum to 1,000 ohm platinum, that same 1 ohm of imbalance produces an air of 0.16, a marked improvement. Okay, let's consider some environmental issues. All of our plants have VFDs, motors, radios, and normal levels of EMI, RFI can cause errors in temperature measurements. Thermocouples and RTD signals are very low-level millivolt signals. When they are direct wired back to the control or data acquisition system, those extension wires serve as antenna for noise. If that noise gets into the signal, it doesn't take a lot of distortion to mess up a low-level millivolt signal. So I encourage you, when you're direct wiring signals, to be sure that you're using best practices to keep noise off those wires. That means drain wires, conduit, proper grounding, physical separation, anything at your means. Or a better solution might be to convert those low-level millivolt signals to high-level signals, and do so as close to the sensor as possible. The same amount of noise will affect high-level signals less than low-level signals. Signals like 4 to 20 milliamps, HART, RS-485 survive most typical levels of noise. Other external influences are shown here. There are times when we head down a path of convenience and end up creating temperature measurement errors. These photos show examples of where a long temperature sensor extends from the thermal well out into ambient conditions. Murphy's Law guarantees the temperature of the probe in ambient conditions will be much different from the process temperature we're trying to measure. So there's a temperature gradient along the metal sheath, and ambient temperatures are wicking away temperature from the hot junction. Or as shown in this sketch, the ambient temperature is hotter than the process temperature, and heat will flow down the solid sheath into the cold process. This will usually cause an offset error, or at the very least, a long time delay in the measurement response. And the solution is simple. We just need to change the sensor configuration such that the solid sheath is totally immersed in the thermal well, and all that ambient temperature error goes away. So we are eliminating this form of ambient error effect. Okay, measurement errors. If you buy modern temperature transmitters or temperature I/O systems from major instrument companies, I think you're going to find similar performance specifications. If you are trying to differentiate some of the finer points between a couple of different instruments, you might want to compare these specifications. I'll just comment on a couple of them. Input resolution, you want the highest input resolution you can find because that says you can detect a smaller change in the sensor's output. So high input resolution sees smaller step changes in the sensor. Long-term drift specs is a measure of the transmitter's stability. RTD excitation current, you want the excitation current to be low because that minimizes the error caused by the self-heating effect of passing a current through a resistor. You want your input impedance to be very high because when you measure millivolts off of a thermocouple or measure those millivolts off of an RTD, you don't want to be drawing any current. And then advanced diagnostics might be a help to you in predicting sensor failures. At the measuring device, when you're looking for the ultimate in measurement accuracy, you've got to deal with the fact that every RTD made still has a slight error in it. And there's a couple of techniques to get rid of that final RTD error. One is a bath calibration technique, and the other is calendar Van Dusen. Both will eliminate that final bit of sensor error. If you put a temperature transmitter or a remote I/O near your sensor, these devices digitize your temperature measurement. If you then decide to send the signal back to the controller data acquisition system via 4 to 20 milliamps, you end up creating 2 more errors. There is a digital to analog error creating the 4 to 20 milliamp signal. And then at the receiving device, there's an analog to digital error in turning the signal back to the digital world. Using HART protocol, the digital signal is one way to avoid these conversion errors. Modbus serial or Modbus over Ethernet is another option to keep the measured value digital. Earlier we saw that using transmitters and remote I/O helped us eliminate error caused by thermocouple extension wire, and to avoid error caused by noise. Now it helps us by keeping the signal digital and avoiding the analog conversion errors. Using transmitters and remote I/O is becoming a common theme. So let's just take another minute and summarize the practical steps we can take to improve our temperature measurement error. Remember, these steps also improve the stability of the measurement, which minimizes calibration expenses. 4-wire RTDs eliminate the error caused by copper lead wire. Use them whenever possible. The cost difference is so insignificant, I would always use Class A RTDs and ones that have been aged through temperature cycling. If the temperature to be measured requires the use of thermocouples, use premium grade thermocouples and premium grade extension wire. Be sure to use noise protection installation techniques whenever you have long extension wire runs, or better yet, get rid of your long thermocouple extension wire runs. This is an error source. Thermocouple extension wire has a finite life and it's expensive to replace. Instead, mount transmitters or I/O as close to the sensors as possible. Avoid the ambient air caused by having solid sheath sensors extend outside the thermal well. Get rid of the final RTD offset error by bath calibrating. Buy the highest accuracy and highest stability transmitter or I/O you can afford. And once you've spent all that money to get your signal digital, keep it digital so you don't introduce any more error. And with that, I say thank you for listening.